Hi, everyone. Welcome to week 2 of Astronomy Geoscience 160 Life in the Universe. This is the first section of Lecture 3, in which we will continue going over some of the basic physics that we'll need to understand the concepts that we'll encounter throughout the course. This section is going to be on quantum mechanics. So, before I talk about what quantum mechanics is, I should explain to you what mechanics is. Dictionary defines mechanics as the branch of physics that deals with the action of forces on bodies and with motion. So the idea here is that if you have a body, such as this baseball, and you apply a force to it with a bat, that will affect the motion of the ball. And knowing what the force is and knowing the characteristics of the ball, we can predict how that ball is going to move in the future. The main equation in classical mechanics, which we also call Newtonian mechanics because it was developed by Isaac Newton, is a famous one called force equals mass times acceleration, or F equals ma. This is the equation that describes the motion of objects we see every day. So it's a little bit hard to understand what this means when it's written like this, but if I rearrange it a little bit, the way you can interpret this equation is that if you apply a force to some mass, and in this case, a force is a shove or a push or a pull, like this penguin is doing to this other penguin, is shoving him down. The mass is the object, so how much that penguin weighs, essentially how much of that penguin there is. That will cause an acceleration, which is a change in the speed. So this car is accelerating from a speed of 0, essentially, to a speed much faster, maybe 60 miles an hour, and as it turns on the accelerator. So the acceleration, for example, that this car sees is equal to the force applied by its motor divided by its mass. The other concept that we need to talk about in terms of quantum mechanics is energy. And again, we're all pretty familiar with the idea of energy. Energy is the thing that powers our electronic devices. We can see it in electric cables and electric wires. But that's not the only way that energy can manifest. So, according to the Khan Academy, energy is a measurement of the ability of something to do work. Energy is not a material substance. So, what that means is I can't pick up and hold energy. I can pick up and hold something that has energy. I can have energy myself, but energy is not something that I can physically hold on to and see. It can be stored and measured in many different ways and in many different forms. And in this slide, I'm showing a couple examples of that. So, for example, if you have a car which is moving, that car has its own energy of motion. As it rolls up a hill, it will convert some of that motion into potential energy stored in gravity. So if something is high up, it holds energy in gravity because if we let it go, then it will accelerate downwards and it will start moving downwards. We can also see energy in the form of motion of this ball. We can see energy from the bat, the motion of the bat being transferred to that of the ball. And we can also store energy, for example, in chemical bonds inside of substances that can then be released as light, such as in this fire here. One of the main principal ideas behind this all is that energy is not created or destroyed. It just changes form from one to another. So you can get motion, energy from motion turns into energy from gravity when something rolls uphill and eventually stops at the top of a hill. And then it can turn back into motion energy when it rolls down the hill and loses that gravitational energy. So classical mechanics has been the way we've used physics to describe the world around us for centuries. Since it was introduced in the 1600s, it has been essentially the way we talk about everything that we can see, in our experience that is about the size of us in our world. And for that reason, it closely matches our experience and our intuition. You and I each have a very finely tuned understanding of classical mechanics, so much so that we can look at images like these and judge for ourselves that, for example, the amount of force being applied by these people hitting each other in the head is not enough to cause them both to fall backwards. We know that because our understanding of classical mechanics shows us that there just couldn't be enough force applied to them to send both of them backwards that way. So we have this intuitive kind of native understanding of how this all works. And this mechanical system, classical mechanics, is so accurate for things roughly our own size that it was what we used to send people to the moon in the 1960s. We didn't use anything more fancy than that in terms of our calculations of physics. But it turns out that classical mechanics has flaws. And in particular, it completely breaks down when we apply it to the submicroscopic world, when we apply it to small particles like individual atoms, and even more so, individual electrons and protons and neutrons and subatomic particles. Instead, if we want to describe these tiny particles, we need to use quantum mechanics. Quantum mechanics is a new theory of physics that was developed in the early 1900s. And the primary equation in quantum mechanics, the equivalent of F equals ma in classical mechanics, is called the Schrödinger equation, which is shown here. So as you can see, the Schrödinger equation is quite a bit more complex than F equals ma, but it's basically doing the same thing. In particular, it has this symbol psi here, which is what we call a wave function, which describes where some particle, anything, a proton, an electron, an atom, a person, might be found. It has a mass of the particle, and it has something that's like a force or a map of force in space, and it combines all of these things together. So in a very analogous way to the way Newtonian mechanics, classical mechanics works, quantum mechanics can describe the behaviors of tiny particles, albeit with these somewhat more complex rules. So in particular, the main difference between quantum mechanics and classical mechanics is that instead of describing where things go, where a particle will be, the Schrödinger equation describes where a wave function will be. And a wave function is a subtly different object than the thing it describes itself. So for example, the Schrödinger equation will not tell me where an individual proton will be 5 minutes from now. It can just tell me where its wave function will be. So what is a wave function? The way you can think of a wave function is kind of like a heat map in soccer. So take a look at this diagram of a soccer field here. The green areas are places where a particular player, in this case a defensive player whose position is over here on the left-hand side of the field, where this player spends most of his or her time. You can see that the red areas are where this player is found often, and the green areas over here where this player would be very out of position are not found very often at all. Another soccer player who plays a different position might spend more time in the front of the field or on a different side of the field. But the same idea applies. If we try to figure out where this soccer player is at any given time during the match, they're much more likely to be found in the red areas than in the green areas. But with only this knowledge, with only the knowledge of this wave function like thing, we can't know exactly where the soccer player is at any given time. We can just guess, much more likely that you'll find the soccer player here than you will to find the soccer player over here. So in the same way, if you look at a particle that's described by a wave function, the wave function tells us where that particle is most likely to be, but it won't tell us exactly where it is. So if this red area is the wave function for one of our particles, for a proton, for example, we can make an educated guess and say that this is a likely location for the particle to be. Here's another likely location for that particle to be. And here's a slightly less likely, but still fairly okay location where we might find this particle. But this one, this is another likely location. But this one over here, we're very unlikely to find our particle in this region because this is in the region where the wave function does not show a high probability. So the wave function tells us where a particle might be and where a particle most likely is, but it can't tell us where that particle will be or where it definitely is. So we can't predict where a particle will be or where it will go with absolute certainty. The only thing we can predict is how its wave function will change. So the implication of this is that quantum mechanics, and by extension the universe, is not deterministic. We can't make a theory, we can't write down an equation that will describe the evolution of the universe forever perfectly. All we can know are the probabilities involved. So don't worry, that may mean that we actually do have free will. So, quantum mechanics as a whole is weird and totally counterintuitive to our experience in everyday life. It has these weird features that I'm not going to have much time to go into, but what I will do is I'll insert a quick video here from a PBS series called Nova Fabric of the Cosmos, narrated by Brian Greene. And once you watch this video, maybe you'll get a better understanding for some of the weird stuff that happens in quantum mechanics.
Quantum mechanics rules over every atom and tiny particle in every piece of matter, in stars and planets, in rocks and buildings, and in you and me. We don't notice the strangeness of quantum mechanics in everyday life, but it's always there if you know where to look. You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them. Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. It's almost impossible to picture how weird things can get down at the smallest of scales. But what if you could visit a place like this, where the quantum laws were obvious, where people and objects behave like tiny atoms and particles? You'd be in for quite a show. Here, objects do things that seem crazy. I mean, in the quantum world, there's a sense in which things don't like to be tied down to just one location, or to follow just one path. It's almost as if things were in more than one place at a time. And what I do here can have an immediate effect somewhere else, even if there's no one there. And here's one of the strangest things of all. If people behave like the particles inside the atom, then most of the time, you wouldn't know exactly where they were. Instead, they could be almost anywhere until you look for them. Hey, I'm gonna have what he's having. So why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
The quantum laws become most obvious when you get down to tiny scales like atoms. But consider this. I'm made of atoms. So are you. So is everything else we see in the world around us. So it must be the case that these weird quantum laws are not just telling us about small things. They're telling us about reality.
Okay, now that we've watched this video, I want to go back to the Schrödinger equation, and I want to take a closer look at it. So in particular, I want to look at these two series of operators that are acting on this wave function here. So this symbol here describes how the wave function changes over time. Does the wave function moving in a different direction over time? Is it getting bigger? Is it getting smaller at any given location? And this symbol here describes how the wave function is different in different places, or how it changes as you move to different locations at the same point in time. These two operations, these two changes of the wave function interplay, and we can use this to solve where we think this wave function is going to go in the future. It turns out that the quantum mechanical solutions to the Schrödinger equation are very similar to solutions of another famous equation in physics. This one we call the wave equation because it describes waves like those you might see in the ocean, or waves you might see in string, or waves you might see in ripples on a pond surface. So this wave equation also has these very similar change operators. The wave equation describes the change of something that looks like the Schrödinger equation's wave function in time, and relates that to the change of that thing in space, in position, just like the Schrödinger equation does. So the implication here is that wave functions, and therefore the particles that they describe, behave like waves, hence the name wave function. So what does that mean for us? Now, it has a lot of very important implications, but the one I'm going to focus on here is the fact that if you have a particle described by a wave function, and that particle is trapped in some place, held very close to some object by some force, then that wave function is going to have particular patterns that it makes. So you can think of this in the same way as you can watch this person swinging this spring up and down. There are only a set number of ways that you can vibrate a spring like this when you have both ends of the spring trapped at some location. So here, this person is holding one end of the spring and the other is being held by a device. And you can make the spring move up and down in this slow rhythmic pattern here. But you can also make it move up and down in a slightly faster pattern. And the idea here is that these patterns are stationary. They're not changing. So you can see here that this region of the spring is moving up and down repeatedly. This area of the spring is moving up and down repeatedly. And in the middle here, the spring is stationary. So this is what we call a standing wave. There's a wave going on in this spring. You can see it. It's going up and down by eye. And it's basically stationary. It's not changing very much over time. And all of the change over time is due to just the imperfections of the setup that we have. The person is moving the spring slightly up and down. So when you have a wave that is trapped like this, you have these particular discrete patterns, and you can count them out. So you have a pattern where there are 0 nodes, 0 places where the spring is staying stationary, basically. The entire thing is moving up and down at the same time. You have solutions where there's 1 node, where there's 1 location in the spring that's staying the same. You have solutions where there are 2 nodes. Here's a node here where the spring is basically staying the same. Here's another one over here where it's basically staying the same. You can have solutions with 4. You can have solutions with 5. And the higher and higher you go, the harder and harder it is to make it show up in a spring. But you can keep going essentially infinitely high in the number of nodes that you can have. But anything in between, any stationary pattern, anytime you try to make a stationary pattern in between these waves, you can't. You end up with some gobbledygook type wave like this that's just kind of moving all over the place. It's not stationary. It's not a discrete standing wave. So the patterns of this spring, the patterns with which this spring vibrate up and down when it's trapped, are discrete. There's only a set number of them, and they're quantized. You can jump from one to the next, but you can't find anything in the middle. And that's how we get the name quantum in quantum mechanics, because the particles described by quantum mechanics also exist in similar quantized states to the way the spring will vibrate when it's trapped. So in quantum mechanics, in many cases, a particle's energy can only take on particular discrete values